Let's do a review of this problem here. We're defined a function in piecewise form, and we're asked to do a few things: to sketch the graph, express it using the Heaviside function, and to solve that differential equation using Laplace transforms. It's in the initial value problem. And this is in the section covering Laplace transforms of derivatives and ODEs. So this is a problem I thought would be much simpler, just trying to pick out problems, but the computation in part C ended up being really long, so let's get to it. Let's hope the video doesn't take too long. So first, let's sketch the graph of this piecewise function. So first of all, let's look at it, at what it says. It says it's going to be 0 when it's not in the range from 1 to 3. So we have a little vision of the domain. 1, 2, and 3. This is t, and I guess the dependent variable would be x, so let's write that there. And 1 would be up here, 2 would be up there, etc. So, at t equals 1, what happens if we plug in t equals 1? Well, at t equals 1, we're going to get 0. Well, t minus 1 squared is a parabola with a root at t equals 1. So basically, it's going to start here at 0, and then what happens when we go up to 2? At 2 is going to be, when t equals 2, it's going to be 2 minus 1 squared, which is 1 squared, which is 1. So it's going to end up at 1. So it's going to end up basically here. Well, it's not closed here, so we'll leave it open. But what happens when t equals 2? When t equals 2, then we go over to 3 minus t, which 3 minus 2 equals 1. So this point is in fact 1. So we know that this is going to be a parabola going up, kind of like that. And 3 minus t is linear. And what happens at t equals 3? Well, t equals 3, 3 minus t is going to equal 0. So it's going to drop down linearly with a slope of -1. So it's going to go down 1 and over 1. So it's going to look like this. And we know that it's going to be 0 otherwise. So 0 otherwise, parabola up to 1, linearly straight down, and then again 0. So this is what our f of t is going to look like. This is our piecewise function. So that's part A. Part B. Let's express it using the Heaviside function. Well, for Heaviside function, I like to write u of t, the unit step function. And it's easier to understand unit step than Heaviside because, well, Heaviside is a name. Well, who knows what's named after Mr. Heaviside. But unit step, we know what the unit step is. The unit step is piecewise function, where is equal to 1 after t is greater than or equal to 0, and 0 when t is less than 0. So it kind of turns on the function at time t equals 0, or whenever this input is. So let's look over here. What happens? Well, it's equal to 0 before t equals 1, but we turn it on at t equals 1. So we multiply by the unit step function at t equals 1, which we do by doing, well, let's look at it here. So f of t is equal, we turn on this part, t minus 1 squared at the time t equals 1. So we write u equals t minus 1. So because what happens at t minus 1? Well, when you're at t equals 1 or below, when you're below t equals 1, then this t minus 1 is going to be less than 0, so it's going to be 0. And then when you're above t equals 1 or at t equals 1, then you're going to have t is greater than, well, t minus 1 is greater than or equal to 0, so this is going to be 1, so this is going to be turned on. So we also turn this off at t equals 2. So what we do is we subtract u at t minus 2. So what does this do? Well, we already know that at t equals 1 or above, this unit step function is going to be 1. So in order to turn it off, we want this indicator function over here to go back down to 0. So how we're going to do that at t equals 2 is that we subtract this at t equals 2, because this is going to be 0 before time t equals 2. But at time t equals 2, then t minus 2 is going to be 0 or above. So then it will have the value of 1. These will both have the value of 1. They'll cancel out, and this will be 0. So that's why this turns it off. So that's our indicator function over here. Now let's go on over to the next part, and it goes by the same principle. We're going to be adding 3 minus t times unit step functions. Well, we turn it on at time t equals 2. So we put in the unit step function of u of t minus 2 to turn it on, and then we turn it off at time t equals 3. So we subtract the unit step function u of t minus 3. So this would be our answer to part B, which is to express f of t using the Heaviside function. So now let's move over to part C. So this might take a while, so let's work it out. So let's first take the Laplace transform of both sides. Laplace transform of x double prime plus x is equal to the Laplace transform of this huge thing over here, f of t. What I'm going to do here is I'm going to do a little, well, I'm going to take a little aside. What is the principle that we're going to use in order to evaluate these Laplace transforms? Well, we have something called the second translation theorem. And this will relate our Laplace transforms and our unit step functions by a power of e. And it basically says Laplace transform of function f of t minus a times unit step function at t minus a is equal to e to the power of negative as Laplace transform of f of t. So this is going to give us a little hint. We already have a lot of functions times unit step functions, and we're going to want the inputs to agree if we want to use this theorem. There's another form of this theorem which will come in handy. Laplace transform when it's just f of t, so you don't have to worry about the inputs agreeing. Then you still have the power e to the negative as times the Laplace transform of f of t plus a. So we're going to use these two forms of this theorem to guide us through this Laplace transform over here. So first of all, we know that the Laplace transform is a linear operation, which means that it allows us to, well, basically act across addition. So Laplace transform of x double prime, this is equal to the Laplace transform of x double prime plus Laplace transform of x. And we know that this is going to be equal to, we know how to take Laplace transforms of derivatives. We learned this in class. So this is going to equal s squared times the Laplace transform of x, let's call it big X, minus s times this initial value, x evaluated 0, minus this initial value, x prime evaluated at 0. And if you remember, we know what these are. We were given that these are both 0. So that's going to be nice for us. Plus the Laplace transform of x, which we said to be big X. So basically, we have, again, we know that these are going to be 0 because of our initial condition. So we have s squared x plus x. So this is going to be s squared plus 1x, where x is equal to Laplace transform of little x, the function of t. So now we need to work on the right hand side, and this is where things are going to get tricky. So pay attention. We're going to have Laplace transform of f of t. So how I'm going to do this is, because we want to use the second translation theorem and we want to get functions times the unit step functions, I'm going to factor out this u of t minus 2 in the middle. So first I'm going to say basically I'm going to rearrange terms first. So first I'm going to say t minus 1 squared times u of t minus 1. And that's nice because again, you see here t minus 1, the inputs agree, so we can use that. Then we're going to factor out the u of t minus 2. So what's that going to give us? Well, we're going to get this, and it's minus this times that. So we're going to have 3 minus t minus t minus 1 squared times u of t minus 2. And then over here, we're going to have minus 3 minus t times u of t minus 3. But the nice thing we can do is, since this is a negative, we can put the negative into here and reverse these two, the order of these variables. And by putting the negative in, we basically add. So we add t minus 3 times u of t minus 3. So now you see we have these two agree, we have these two agree, and now this one is going to be the tricky one. So we have a little bit of an idea of how we're going to solve the problem. So let's see here. Well, we're going to use the linearity of the Laplace transform again to split up the add-ins. I think that's what's called add-ins. Well, L of f of t is equal to Laplace transform of this thing u of t minus 1, this thing, plus the Laplace transform of this thing. This, well, first let's simplify this a bit. 3 minus t minus, well, t minus 1 squared is t squared minus 2t plus 1. So if we minus this out, we get negative t squared. We get plus 2t minus t, we get plus t. We got negative plus 1, so that's minus 1. 3 minus 1 is plus 2. So that means in here we got, having simplified that out, we got negative t squared plus t plus 2 u of t minus 2 plus the Laplace transform of t minus 3 u of t minus 3. So we have this now. And again, let's get our second translation theorem. So gives us a way to evaluate this. Laplace transform of f of t equals, so this is going to be basically e to, if we look at this, a is going to be equal to 1 in this case, f of t is going to be equal to t squared. It's going to be e to the power of negative, a is 1, so negative s times the Laplace transform of f of t is going to be t squared. Okay, so now we go on to this one. This one is going to this one is going to require our second form of the theorem. So we have, because the inputs here don't agree, so this doesn't look like a t minus 2 thing. So we have that e to the negative 2s out front, since a is 2 now, and the Laplace transform of, so f of t plus a. Well, f of t is this, so if we say that f of t is this, well, let's do a little algebra first to simplify. If we say that f of t is negative t squared plus t plus 2, then f of, well, we're going to need t plus a, so t plus 2. F of t plus 2 is going to be negative t plus 2 squared plus t plus 2 plus 2. So this is negative t squared minus 4t minus 4 plus t plus 4. So these things cancel out. And the t over here combines to make negative 3t. So let's write it nicely over here. It's going to equal Laplace transform of negative t squared minus 3t. Okay, and now let's move on to this, which is relatively simple. We have a is equal to a over here is going to be equal to 3, so we have e to the negative 3s times the Laplace transform of, well, it's going to be just the function t. So now that we have this, let's continue. So now we have, let's remember what L of f of t is equal to. L of f of t is equal to this, which is equal to this, which is equal to this. So this is going to be our s squared plus 1 x is going to be equal to, well, hopefully you know how to do these. So e to the s, the Laplace transform of t squared is going to be 2 factorial, which is 2 over this power plus 1, which is 3. So it's going to be e to the s times 2 over s cubed plus, I'm going to leave that in there to make our partial fractions easier. So negative t squared, again t squared is going to give you this, so negative of that is negative 2 over s squared over s cubed. Negative 3t, well, the Laplace transform of t is 1 over s squared. So if you multiply s on top and the bottom, and then you multiply by that factor of negative 3, you get negative 3s s over s cubed, or s squared. So that's this. Over here we have e to the negative 3s, and the Laplace transform of t again is just simply 1 over s squared. So now, by now, you probably know what's going to happen next, and it is going to be tedious, so let's continue through. X is e to the negative s times 2 over s cubed, s squared plus 1, plus e to the negative 2s. Well, the reason I'm doing this is because I'm dividing this over everything, so we can isolate the x. So yeah, divide by the s squared plus 1. Let's rewrite this as negative 3s minus 2 over s cubed, s squared plus 1, is e to the negative 3s. So the reason I'm writing it like this is so that we can have a form for us to do partial fraction decompositions. So as you might have imagined, we're going to have to do partial fraction decomposition 3 times. So, well, let's get to it. Let's get to it. So 2 over s cubed times s squared plus 1. Well, we know that it's going to be in the form a over s plus b over s squared plus c over s cubed. It ascends by the powers. ds plus e. It's the polynomial degree below polynomial that's on the bottom. So what happens here? We're going to multiply by whatever the common denominator is. So we're going to cancel out the 2 by multiplying. Common denominator is s cubed s squared plus 1. So we knock out that denominator. A times, well, what we can do is first we can, well, I'm going to write it like this. Because you cancel out powers of s respectively, and then you multiply the whole thing by s squared plus 1, and then you cancel out this, so you get ds plus e. I might get fast here and a little sloppy because I don't know how long my video is running, so I don't want it to take up forever. As squared, as to the 4th, plus we're distributing it out, basically ratioing each of these variables by power of s to the power of 2, and then just s by itself. Then over here, distribute that. So as you expect, well, there's a little tangent. Well, you know that this is going to be a polynomial of degree 5, so you would expect to have 5 variables. So if you're thinking that this is maybe a bit tedious, then you at least know it's justified. So let's look at this. Well, in the method of partial fraction decomposition, what we do is we have this polynomial here, and we want to equate this polynomial to this constant one here. So since this polynomial has a bunch of powers of s, we know that all their coefficients are going to be 0. So that gives us some help. So the only constant term that we have on this side is going to be this c, if you look over here. So we know that c is going to be equal to 2. Let's collect the like powers. This is the fourths, a and d. So we know that a plus d equals 0. The cubes over here. These are the squares. And this is a single b, so well, this is going to be b equals to 0. B is equal to 0, so b plus e is equal to 0. B plus e equals 0, where b equals 0. So e equals 0. So e is going to be 0. C is equal to 2. A plus t is equal to 0. And a s squared. This over here is going to give us a plus c is equal to 0, where we know that c is equal to 2. So c is equal to 2, so a should equal negative 2. If a equals negative 2, then d should equal 2. So we have it over here. A equals negative 2. Let's rewrite our function. 2 over s cubed times s squared plus 1 is going to be equal to negative 2. Plug everything in to the proper form. We have no b, and our c is 2 over s cubed. Then d is simply 2. So 2 is going to be s over, I'm going to write it sideways like that because it's easier to see how it applies to the inverse Laplace transform. So basically we have that. Yeah, let's continue. We have over here, this is probably going to be the ugly one, so that's why I decided to keep it as negative negative rather than factoring out the negative. So well, let's get to it. We have the same denominator as this one up here, so I'm just going to use a little shortcut. They're the same process. We're going to have the same form anyway, so as to the fourth bs cubed plus cs squared as squared plus bs c plus ds to the fourth is es cubed. Again, we're going to collect powers 4. A plus d is equal to 0. Powers of 3. B plus e is going to equal 0. Powers of 2. A plus c is equal to 0. bs plus c is going to equal these. These are the only linear and constant terms, so b is equal to negative 3. C is equal to negative 2. Okay, so we have stuff to work with. Negative 2, c equals negative 2 gives us a over here is equal to 2. A equals 2 over here gives us d equals negative 2. B equals negative 3 gives us e equals 3. So now we have this huge negative 3s minus 2 over s cubed times s squared plus 1 is equal to, we can plug in the variables into their proper forms, like over here again. 2 over s minus 3 over s squared minus 2 over s cubed plus negative 2 s plus 3 over s squared plus 1. And I'm going to check my notes. Yeah, looks about right. Looks about right. So let's continue onwards. We have one more to go. So we did this one, and now we need this one. So now let's look at, this one should be relatively straightforward. 1 over s squared times s squared plus 1 is equal to, go up the powers, but you don't have to go up to s cubed this time. So now we only need 4 variables. So what happens if we multiply by the common denominator, which is s squared plus 1? Well, we're going to get, again, 1 is on the left, on the right is going to be as plus b times square root plus 1 cs plus d times s squared. So this is going to be as cubed plus bs squared plus as plus b plus cs cubed plus ds squared, and this is going to have to equal 1. So again, let's equate coefficients and see what we get. We have one single linear term, which is a, so we know that this is going to have to equal 0. If a equals 0, well, this is a power of 3. The other power of 3 is c, so c must equal to 0. The only constant here is b. b is equal to 1. b s squared powers, well, e plus d equals 0 basically, so that means that d is equal to -1, and we got our 4 variables, so that means that 1 over s squared plus 1 is equal to 1 over s squared minus 1 over s squared plus 1. So now we have everything we need in order to proceed with our inverse Laplace transform. So we're going to work off what we had over here. So we're going to take the inverse Laplace transform of both sides to get our solution that we wanted, which is the function of x, function x of t. Function x of t. This is going to equal the inverse Laplace transform of big X, which again we said was a Laplace transform of x, so inverse of the operation, we get back the original. So now we're going to take the inverse Laplace transform of this huge thing over here. And well, we already know that the inverse Laplace transform operator is also linear, so I'm just going to basically pull out the addends, so whatever they're called. Things separated by the terms separated by the addition sign. So again, that this is equal to, this is where we use the result of our partial fractions. Negative 2s plus 2s cubed plus 2s over s squared plus 1. And then plug in what we had over here, up here, so inverse Laplace transform e to the negative 2s times 2 over s minus 3 over s squared minus 2 over s cubed plus negative 2s plus 3 over s squared plus 1. Hope the video isn't taking too long. And then inverse Laplace transform of e to the negative 3s times, what was this? Well, again, it's up here. For s squared minus 1 over s squared plus 1. So now we know our function of t is basically this, and that's our answer. So yeah, let's use what we know to simplify this into something more useful. So again, we have our second translation theorem. So we're going to basically work the second translation theorem in reverse. And how we're going to do that is, well, we know that if we have something like this, well, let's rewrite the second translation theorem. So we're going to have the inverse of this, and it says that the inverse Laplace transform of the negative s Laplace transform of f of t should equal to the inverse Laplace transform of that, which is f of t minus a, unit step of t minus a. So, and of the other form, it would be e to the Laplace inverse Laplace transform of this So let's see what we can do here. Well, first let's find out what are these as Laplace transforms. So basically we'll take the inverse Laplace transform of these and see what we can get. Functions of t, Laplace transforms of functions of t, and then we'll see which of these inverse forms we can use. So x of t is going to be equal to, maybe that was a bit of a complicated explanation, so let's just do it in practice. So this is the Laplace transform of what? Well, 1 over s, we factor out the negative 2, so we get negative 2 times 1, negative 2 times 1, plus 2 over s cubed. We know that that's the Laplace transform of t squared, and then plus 2 times, you know that this is the Laplace transform of cosine of t. Cosine of t. So we have something that can fit one of these forms. So the negative 2s. This is the Laplace transform of 2. This is the Laplace transform of 3t, because the Laplace transform of t is 1 over s squared. This is the Laplace transform of minus t squared. This over here, we're going to factor out the negative 2 times the s over s squared plus 1, so that's going to be a negative 2 times, again, s over is going to be cosine of t. 3 over is going to be 3 times sine of t. Laplace transform of this, plus the inverse Laplace transform of e to the negative 3s times Laplace transform of t minus sine of t. Now we're almost done. X of t is equal to Laplace transform of this, so it says that when we have this form, then we're going to have to take whatever the a is, which is, in this case, is negative 1, negative 2, negative 3. We're going to have to take the a, put it into f of t minus a, where this inside here is f of t, and then multiply by the unit step function of t minus a. So basically this function here, we're going to evaluate this at t minus a, where a is equal to 1. So this is going to equal to negative t plus t minus 1 squared plus 2 of cosine of t minus 1 u of t minus 1. Next, this is going to be this evaluated at t minus 2, so 2 minus 3 times t minus 2 minus t minus 2 squared minus 2 cosine of t minus 2 plus 3 sine of t minus 2 times let's squeeze it in here, unit step of t minus 2, and then finally this evaluated at t minus 3 minus sine of t minus 3 u unit step of t minus 3. And just to make this a little bit nicer, we're going to do a little algebraic simplification. So if we first look up here, negative 2 plus t minus 1 squared, well, this is equal to t squared minus 2t plus 1. So that this minus 2 plus is going to make that equal t t squared minus 2t minus 1. Over here we have 2 minus, well, if you distribute the 3, you're going to get minus 3t plus 6. Then this is going to be negative t squared minus 4t plus t. Over here, you can't simplify this part. So we're going to have a negative t squared. Then this is going to be plus 4t and then minus 3t, so it's just going to be plus t. And this is going to be 2 plus 6 is equal to 8 minus 4. So that's going to be 8 minus 4 is plus 4. And that is just simply, that's good. So it might have been a bit messy, but let's rewrite it here one last time. Finally, once and for all. Let's write in brackets to make the thing clear. Plus 2 cosine of t minus 1 u of t minus 1. So the solution is going to turn on this function at time t equals 1. And then at time t equals 2, it's going to turn on this nasty thing. Negative t squared plus t plus 4. 2 cosine of t minus 2 plus 3 sine of t minus 2 u of t minus 2. Then at time t equals 3, it's going to turn on this other thing, which is t minus 3 minus sine of t minus 3 u of t minus 3. And finally we can circle this, say we have our solution. And I know this looks like a huge, nasty solution. Let me just check with my notes. Yeah, so this is a solution that I've already checked beforehand, so, and that was already quite tedious. So this over here is the solution to our part C. And just as a little bonus, maybe let's give this a little bit of, now that we've already spent so much time, let's give this a little bit of intuition. Let's say that this function over here, x double prime plus x is equal to f of t. We can say that this models a mass spring problem, or this models a the LRC, RLC circuit problems, where f of t is a forcing function. So if the forcing function looks like this, which is given by this piecewise function, and we give it a force that looks kind of like this function, whether that force is in the form of moving the spring when it's in a mass spring problem, or when it's giving it a voltage when we're doing a Kirchhoff's law problem, then that's an interpretation of what we're solving. We're solving for the function of time, the model of motion, or the model of current that results as a function of time. So that's basically what we've done here. And well, man, it's been about 38 minutes, and I hope this video has been helpful.